I don't even know about actually. So, it's such a pity that I worked on that slide. I talked to a friend of mine. So yeah, so yes, everyone should have it clear. Two important points. One is that the outer page table, remember what we're talking about, outer page table? It has to be contiguous. Or maybe I'll draw that on the board.
Your code stuff.
You see, if I have, now this is the outer page table, and then it goes to these pages, right? And then these pages, well, let's start with the one level. One level would be like this, right? This would be called the page table, and these would be the pages, right? So if I am at this line, I'm gonna have an address like this. It's gonna have a P and a D. What is the D? Offset. What does the D tell us? The size of the D tell us.
The size of the page.
The size of the page is very important, right? The number of bits here tells us this size of each page, because this is just going to tell us which page to go to, and I need to know which block of memory, which byte of memory in there. So I need to be able to address every single byte. So the size of it is due to be a fixed, relationship to this D. If this D is okay, so let's do a quick math. If this D is 10 bits, how big is the page table?
2 to the 10.
2 to the 10th, which is, should remember this.
1040.
1 kilobyte. Remember, every 10 is a kilo, 20 is a mega, and 30 bits is a giga, and 40 bits is a tera, and 50 bits is a peta, if you're going that far. Yeah? So this is 1 megabyte, 1 kilobyte page, 10 bits. If it's 12 bits, then how big is it?
4 kilobytes.
4 kilobytes. Everyone, yeah?
I'm down on the piece of that. It's
What?
just a math thing, but like maybe my math is off. How do we get from if 10 is
10 is 1 kilobyte.
Yeah.
2 more bits is like multiplying it by 2 to the 4th. 2 to the 2, 2 to the 2, 2 to the 2 is 4.
No, yeah, I get how you do that math. I'm just practically like, meaning if we have 10 bits, we'll say this big, then add 2 more.
So every time we add a bit, 1 bit, we double the size of it. So what's, right?
We double it.
The size of it.
The size of 10.
Of what we can address.
One second. I'm just confused. Like, practically, I'm confused. Like,
Yeah.
we have 10. Let's say 10 is this big.
10 what?
10 bits.
Bits or 10 bits?
10 bits. Like just
I mean,
imagine, like
the
I
page
visualize
size,
it in my head.
the page size.
Yeah.
You're right. Once we say it's 12 bits, now the page size is going to be, what if it's 11 bits?
Yeah.
Then it would be this big. It would be, well, it would be
Double.
twice as big.
11 is double 10,
11 is double 10.
and 12 is
Because
double
every
11.
bit is multiplying by 2.
Oh.
Just like in decimal, if you add another digit, if I get a check for this much, it's $100.
Right.
If I add another digit, then I multiply by 10.
Right.
Because it's base 10. If I add another digit, now I got $10,000. That's because I added 2 bits. I multiplied by 10 to the squared. 10 times 10, multiplied by 100. So the same thing with base 2. Every time I add a digit, I multiply by 2 instead of by 10.
Okay. Thank you.
Sure. Where's my eraser? Okay. So, okay. So if it's 10 bits, it would be 2 kilobytes. If it's 12 bits, it would be 4 kilobytes. And the outer page table is this, is going to be contiguous. Now, if this is, I'm just doing this again. If this is 32 bits, I'm left with 20 bits. So the two questions I have to ask you. How many rows are there in the outer page table?
2
Wait a second. So the 2 to the
20.
20th, 2 to the 20th rows. Is that clear to everybody that it's 2 to the 20th row? Why is it 2 to the 20th rows? You tell us.
Same way that to, as in,
In other words,
I can address to 2 to the 20.
because this number tells me how big the pages are. This number tells me how many pages there are. There are clearly 2 to the 20th pages. If I'm going to have a row for each page, I'm going to have 2 to the 20th rows. True?
Because each bit of the 20 bits can be 1 or 0. So it's 2 of them.
Right. There's the first one. Now, if this is all zeros, then I'm going to the first row. This is all zeros and a 1, then I'm going to the second row. This is all zeros and 2, then I'm going to the third row. Now, here is the thing that we were a little bit confused with last time, and I want to make clear now, which is how long is each row? How long is each row? Well, each row, what's the minimum size of each row? Here's the page table. How long is this row? From 0 to what? How many bits in this row? Minimally.
20.
No, not 20.
How many
What does each row got to tell me?
how many
Oh,
pages?
sorry. You're right. Sorry. We didn't think about that again. Yeah, you're right. Because, yeah, Zava's right. It's 20. Because this is telling me 0, 1, but each of these rows is telling me which one to go to. Because it could be that I write here 0, 0, 0, 0, 1, and I mean to be the second row, this row. But now I'm on the second row. I got to go to a particular page. And that page is one of 2 to the 20th pages. So I have to have 20 bits here to specify it. So it's got to be at least 20 bits. Is that true?
How could it be more?
How could it be more? Well, it could be that, so this is actually an excellent question. Zahava asked, how could it be more than 20 bits? And it will always be more than 20 bits. Why will it be more than 20 bits? What?
Valid.
Validity bit, exactly, valid bit. It's going to definitely have a bit here, valid. Can you guys, know me? I mean, can Gabi and etc. hear me? I don't know what you guys see because I didn't share my screen.
They see the camera.
They do? They see the camera? Good.
At least
Okay.
in my screen.
So this has got to be, what did I write, 2 bits here? 20 bits. 21 bits. So it's really 21 bits. It's got to be at least 21 bits. 21 bits. What is the valid bit? Now, this is a very key point, which was emphasized in one of those videos that I sent. The MIT one, I think, in particular, we talked about. Really, even though this is, remember, this is a page table. How many page tables like this do we have in our operating system? All right, first of all, I want to say, the operating system is the one that's deciding on making pages. And therefore, the operating system can say, I'm going to keep the page table contiguous. I'm not going to divide it up, because he's the one who made these divisions anyway, right? Al-Topesh Asar Ken Matir, as the rabbi said. It's a Gezerah, the rabbi, right? Anyway, he doesn't have to page this, so this is going to leave, but the operating system has this in memory. He essentially created an array. He created a big array called this page table. And how many of them is he going to make? How many of these page tables is he going to make?
As much as one for each.
As much as what?
One for each.
One for each
process.
If there's 100 processes, he's going to have to make 100 of these. Why? Because each process thinks that he's starting from the beginning of the memory, just like we did in MIPS. In MIPS, your array was at the beginning of the memory, and your next array was right after it. Each one thinks that he's at 001, 002. So I need to have a page table tell them, oh no, I need to map your 001 to this page, to that page. So he's going to have, everybody's going to have his own mapping of where those virtual addresses really are in a physical address space. But what does that mean? Actually, I'm not going to give physical memory, the whole physical memory to every process. Every process is going to have a small piece of the physical memory. Most processes are very small. So what's going to be, and most of these pages here is going to be 0, not valid, not valid, not valid. Almost everything is going to be not valid. I have to keep those rows of the page because maybe one of them will be valid. But essentially, because maybe he actually does want to jump to some future place in memory, and I need to tell him where that is. Maybe his program is jumping way ahead in memory for some reason. So some of them, so I have to have the page table. But the ones that are invalid, do I need to allocate them? Do I need to actually, the ones that are invalid, this one is invalid. That means I'm not, if I get there, the operating system is going to say, sorry, you can't go there. Is it going to be pointing somewhere? No. So this page table, while I do have to allocate this, I'm not, all these, a lot of them are invalid. And therefore it's not taking up memory. It's not like all this is active. It's really like, more like this. In other words, I just have, some of them, right? This one is valid, so he's pointing here, and maybe this one is valid. So I may only have 3 pages, but for each process, I'm going to have a page table. I'm going to have a page table. So wouldn't it be nice if we could, wait, sorry. I was still in the middle of explaining this 21 bits. So back to this 21 bits. It's 21 bits long, and we had this problem last time, which was like, well, if I say 1 here, that means go down 1 row. If I say 2 here, go down 2 rows. Now nobody talks about this question, but it interests me. And this question is, but wait a second, if that's a 1, and this is not 1 byte later, this is 21 bits later, which is much more than 1 byte, right? A byte is only 8 bits later. This is like, how are we going to translate this one first row to be this first row where it's how many bytes I got to go forward? You see what I mean? I have to make a translation.
Can it be hard coded to just know? Well, however big the rows are, like instead of jumping one
right,
byte,
you
jump one
just
row.
right. You could exactly. So it has to be. So in the software of the operating system, that's the question. In the software of the operating system, he's going to have to do some kind of calculation. He's going to have to say, wait a second, it's 1, but that really means 21 bits or 21 bits forward, which is, well, but that's slow to do a calculation. That means we're going to have to, every time we do a memory access. Every time we do an access, we're going to have to do a mathematical addition, and we want to do this super fast. So we want to, whenever you hear the word super fast, what should pop into your head? How do you do it? Cache, that's a good answer. But what else? What's the fastest thing? Then rather than software calculations? Hardware. We want hardware to make this jump. So hardware isn't going to be, so the easiest thing for the hardware to do is just to add 2 zeros or add a 0. So therefore, that's why we're going to round this off into multiples of 2. So if this is 21 or multiples of 2 to the power, 2 to some power. So it's always going to be 2 to some power. So 21 bits is how many bytes? It's 8 is 16. It's 3 bytes, right? It's minimally 3 bytes. So we're going to call it 4 bytes. So, right? Okay. It's 3 bytes. 3 bytes is 8 is 16 plus another 8 is 24. So that's more than 21. But we're going to actually call it 4 bytes, which is 32. We're going to make this 30. We're going to make this a little bit larger, and we're going to call this 32 bits, and a lot of them will be unused, but that's okay. And then we're going to have a number here that says 1. And what are we going to do when we get 1? We're going to just turn it into 0, 0, 0, 0, 0, 1, 0, 0. We'll have the wires that are coming in have 2 more extra wires with zeros on them, and then that number will take us automatically to this row, because this is 0, 1, 2, 3, 4, and that's 4. You see? So we will have, so the number here will be 1, but we'll be able to use that 1 to get to the 4th byte, okay, by adding 2 zeros, and then to the 8th byte. So yeah. So actually, yeah.
The 5th byte?
5th byte, yeah.
Oh, yeah.
Byte number 4, however you want to call it. Byte number 4 or the 5th byte. Yeah. So because 0, 1, 2, 3, 4. So we'll keep on adding 2 zeros. Is that clear? So that way we'll be able to get, so that means, okay, so that's why the book and most of the people just talk about this is 1, tells us to go down 1 row. But I was interested in how exactly that works. So this is how it has to work. And why I'm interested in how that works. Not just because I also teach architecture, but because it defines for me the size of the page table. And the page table I don't want it to be too big. So I'm interested in knowing exactly how big it is at every moment. According to this architecture, it's going to be quite large. It's going to be 32 bits. Let's think about this. How big is it going to be? 32 bits or 4 bytes. 4 bytes or 4 bytes, or let's say 2, what is 32 bits? Right, 4 bytes. So 2 to the second bytes, which is 4 bytes. 2 to the second bytes times how many of them do we have?
2 to the 20th.
2 to the 20th. So that's going to be 2 to the 20th, but we already know what's 2 to the 20th. Mega. So it's a mega. We have a mega row. I don't add the word byte because we have bytes to remove, bytes squared. We don't want. But it's 2 to the 20th is 1 mega, and this is 4 bytes. So how big is this going to be?
4 mega.
4 megabytes. That's how big the page table will be. 4 megabytes, which is crazy. Think about why is that crazy? I could have a process that's just doing some little tiny thing. It's a tiny 3-line program or a 100-line program. 100 lines is nothing. 100 lines is less than a kilobyte, right? It's nothing. And how big is the page table for that guy?
The page table.
The page table.
Memory. It's not even the actual memory.
It's just the mapping for the memory. It's just the page table, just to map it is going to be 4 megabytes. So that means that every process, no matter how small it's going to be, is going to at least use 4 megabytes of memory.
Why is it always?
Which is terrible because I may have hundreds of them. Why is that? And imagine, and this is only in a 32-bit architecture. Imagine if I had a 64-bit architecture, then this table would be much longer. How could I make the table? Wait, so you had a question.
I'm gonna ask, what if like you have a very short program, can it just cut off? Meaning like.
Can just say the rest of the page table we're not going to keep because you're not using it.
Yeah.
It's a good, theoretically, I guess it could.
It's just gonna be empty, and you don't really need that. Like you just need enough lines for your code.
No, because I would have. You're right, because I would.
Anyway, we're like in the page table. It's.
No, I'll tell you what. There's a problem with that because how is it going to? Because it could be that in my program, I'm a bad programmer, and I wrote load word, and I put some huge number there. It's a 4-line program, and my first line of it is load word at place billion. I can write that.
Okay,
And then what's going to happen? He's going to add the 2 zeros. He's going to go to the page table. Now, really, the page table doesn't exist. But he's going to have some line here that doesn't say 0001. It's going to say 1, 1, 0. It's going to be some large number. And he's going to add the 2 zeros, and he's going to go down to this row, which doesn't exist. And he's not going to find an invalid bit. You know what he's going to find? He's going to find that he's in somebody else's page table. And he's going to go to some other memory. I need to be able to tell that programmer, you have reached an invalid page. You know what I mean? I need to be, those invalid bits, I need them so that the programmer won't violate his memory space. You understand? You ever heard that question? An interesting question. Why do I have to have it? And my answer is I do have to have it so that he doesn't go to memory that he's not allowed to go to. So how can I make the page table smaller? Simple solution. How can I make this page table smaller? Without changing anything about this. Well, changing one thing. What can I change over here to make this page table?
So you would add an extra P and make another.
No, that's one way. But before we get there, what would be the first step? What would be the most simple way to make a page table smaller? Remember, we divided this in 12 and 20.
Make the rows bigger.
Make the page tables bigger. If the page tables, instead of being 12 bits, are 22 bits, huge page tables, right?
I thought, wait, page tables or pages?
Sorry, pages. Sorry, make the pages 22 bits and make this 10. I can make this 22 bits, right? Then the pages would be really big. How big would they be? How big would they be if they're 22 bits?
4 megabytes.
4 megabytes. It'd be 4 megabytes.
Or anyway, we can say on mistakes.
So, yes, so.
Either way, we're wasting it.
You're right. So we can try to find, so let's not do 22, let's do 20, okay? Let's do 20. And then what do we have? We have 1 megabyte pages. And a small program will certainly fit in 1 megabyte. how big will the page table be? It'll be 12,
4 kilobytes.
12, so it'll be 2 to the, so it'll be what? It'll be
4 kilobytes.
4, 2 is the 4. So it's like it's 10 now. 10 is a kilo. So 4 kilo rows, it's 4 kilo rows, but each row is 4 bytes. So it'll be 4 times 4 is 16. It'll be 16 kilobytes. Somebody want me to repeat how I got to 16 kilobytes?
It's 4
Yeah.
megabytes times 4 kilobytes.
No, forget the 4 megabytes. That was the old calculation.
Oh.
Because if this is 20, then this must be 12. It's 32 bits. This is 12 bits. What is 12 bits? 12 bits means how many rows I have. I have 12 bits. I have 12, 2 to the 12th rows. What's 2 to the 12th rows? It's like writing 2 to the 10th rows times 4. Because 2 to the 12th is 2 to the 10th times 2 to the 2nd. Because you add the exponents. So I can separate the exponents. I can say it's 4 times 2 to the times 10 bits. 10 bits is a kilo. Every 10 is kilo, 20 is mega, 30 is giga. So if it's 10 bits, it's 4 kilo rows. I notice I don't write bytes. It's 4 kilo rows, 4,000 rows, essentially, about. But remember, it's not 1,000, it's 10 to 24. So it's 4 kilo rows. 4 kilo rows. But each row is 4 bytes. So each row of this is going to be 4 times, it's not 4, it's going to be 10 times 4 bytes. And now I can add the word bytes. It's 4 kilo rows, 4 kilobytes, but I have to add the 4. 4 times 4 is 16. I get 16 kilobytes. 16 kilobyte page table. Because I'm having, 4 kilo rows, and each one is 4 bytes long. 4 times 4 is 16. 16 kilobyte table. So actually now it's great. Now I save space, right? I have 16 kilobyte page table, tiny page table. That's great. It's not
It
4. It was 4 megabytes before.
But
Now it's 16 kilobytes is nothing.
But it's
And the page tables are only 1 megabyte. Great. But what's the disadvantage here? I mean, it's better than before. For sure, it's better than before. But what's the one?
Will the access times be different?
No.
Because the pages themselves are so much bigger.
So what? I'm just going to jump to the page based on the offset. I'm just going to jump to that line. Doesn't matter how. I got my offset. I'll just jump to that line. Doesn't matter whether I'm jumping 100 or jumping 1,000.
But then the amount of space though being taken as opposed to being a bigger page, a smaller page and bigger table. Now you have a smaller table, bigger page.
No, but think about the minimum program. Think about the minimum program just as Hello World. Whatever. The smallest possible program. Maybe Hello World is not the smallest program, but the smallest possible program. 1 plus 1 equals 2.
So why does it need such a big?
So it's going to, now how much is, in the previous scheme, it's going to take 4 megabytes plus a kilobyte. Now it's going to take 1 megabyte plus 16 kilobytes. It's going to be smaller. The smallest program will be smaller. So that's great. So that's a better, now somebody might say, yeah, but you did it good, Nachum, because this is only, what is this? This is 1 megabyte, or sorry, 20 byte, yeah, 1 megabyte. But you can, it seems dumb to allocate a minimum of a megabyte to a program. There's no program can have less than a megabyte. The minimum I can access, the previous one I could give them 4 kilobytes. As much I could make small programs small. Now small programs will take, and I'm saying, yeah, well, I'm saving space on the page table, so it's worth it for me to waste. But it's I'm just saying what's written in the books is that the problem with making this too big is that you now have what's called a lot of internal fragmentation. You're going to have to allocate to people groups of megabytes, even though they may only use 1.1 megabytes. You're going to have to use 2 megabytes. If they really only want 1.1 megabytes, I'm going to have to give them 2 megabytes. So as the pages get bigger, the internal fragmentation gets bigger. Everyone sees that? Internal fragmentation. In other words, what's allocated to them. So so that's that. Now let's talk about another another thing, which is what we talked about before, really drilling this into your head, I guess, which is two-level page table. You see, sorry, if I had 60, I mean, I don't want to go through all the math of it, but if this was 64 bits, then I would run into troubles no matter what, right? However, if I divided, if I make 20 bits here, then I'm gonna have to have, wait, 20 was what we had before. Let's say I make 30 bits here. Let's say this is 29. I have 30 bits for a page. Now all of a sudden a page is how big? A gigabyte. Well, that's crazy. Every program, the minimum program would have to allocate a gigabyte to it. So let's put it back at a megabyte. Let's put it back at a megabyte. 20 bits.
Then your page
So then, exactly. So now it's back to a megabyte, which is reasonable. 1 megabyte pages, but I'm left with how many bits for my page table? 64 minus 20, 44 bits. Well, 44 bits is how big? 40 is what? 40 is what? 30 is, 10 is a kilobyte, 20 bits is a megabyte, 30 bits is a gigabyte, terabyte. So this is to the fourth, 16 terabyte page tables. That's insane, right? That is impossible.
If you have such a large number, like I'm saying, you can handle it.
No, I can't. In memory. 16 terabytes of memory? No computer that you've ever seen has 16. We're talking about 16 gigabytes of memory. This has to be in memory, not on disk. 16 terabytes. This is insane. It's totally insane. Everyone sees that? So I have to make the pages bigger, but that's also going to be crazy. Even if I make them bigger, then they'll be gigabytes. Then the minimum program will take up a gigabyte of memory. So this is not tenable, not workable. No matter how we divide it up, it's not going to work in a 64-bit architecture. Yet everybody here has a 64-bit computer, and it's working, and it's not taking, and minimum programs are not taking terabytes of memory. So how do they do it?
The two-level.
So that's where we get to the two-level one. So what we have to do is let's leave it at 20 megabytes, even though it's huge. Really, that's considered a large page. But let's leave it like that. And we're gonna go like this. We're gonna say, and here's where it gets a little, that was all easy. That was all easy what we just did now. So I hope you're paying attention. But now we're gonna get more complicated because we're gonna have a page table. In other words, what we're going to do is like this. Let's keep it 20 and 20. Let's, let's say 20. We'll have to see how it's going to work out. Actually, there's a rule for how it has to be. Before we make this number, let's figure out how it has to be. Each page before we go here, how many, in order to identify these megabyte pages, how many bits do I need? In order to identify them, back to the same question we asked before. We asked the same question when we had 32 bits. If I have 1 megabyte pages, they're taking up, each one has 20 bits of data in it. In other words, 1 megabyte of data, which is 20 bits. What we call the address space is 20 bits. But how many of these do I have? How many of these do I have? I got a lot of them, right? How many? I should know exactly how many. Tell me how many. Shira, how many? Sorry, Abigail. I get confused. Abigail. No, that's how big each one is. But how many of them do I have? It's the remainder bytes. This is a 3.
Oh, the 2 is,
This is 64 bits. 64. 2 to the what?
60, wait,
No.
40.
40, a little bit more than 40.
43,
What?
43, 44.
44. Because remember, the 64 bits, I just wrote it from 0 to 63. It's 64 bits. If 20 are used up, then 44 are left over. So it's 2 to the 20, 2 to the 44th. That's how many pages I have. How many pages do I have? I have 2 to the to the, which is what, how much is 40? How we go? How many, is it mega? Is it kilo? Is it giga? Is it tera? Is it peta? I'm just trying to get your mind, get the oil, heat up the oil there, so the gears work better. Well, 10 is a kilo, 20 is mega, 30 is, what's after mega? Giga. And what's after giga? Tera. So this would be to the fourth, it wouldn't be 4, don't say 4 tera, say 2 to the 4th tera, which is 2 to the 4th is 16, right? So 16 tera. So these will be 16 terabytes. Just stop and say 16 tera. No. So the answer is, well, 2 to the 24th or 16 tera, not terabytes, 16 tera. 16 tera pages. Okay, that's just pointing out how many I have. But how do I, if I've got 2 to the 24th, if I got 2 to the 44th of these, how many digits do I need to identify each one? I'm just asking the same question in a different way. How many digits do I need to identify all of these 2 to the 24th? Well, the first one will be called 0. Second one will be called 1, 0, 1. Next one will be called 1, 0. The next one will be 1, 1. I'll need 44 bits to identify all of these pages. One of them will be called 001. So the number of bits that I need in my page table is 44, plus a valid bit, so 45. True? How many bytes is that? If we're going to make a row of that, and remember, it has to be a multiple of, it has to be a power of 2. So it's not going to, is it going to fit into 4 bytes? What's 4 bytes? That's 32. It's not going to fit into 4 bytes. It's going to be 8 bytes, right? If 4 bytes is only 32 bits, and this is more than 32 bits, it's going to be 8 bytes long. So that means each row of the page table that's referred to this is going to be 8 bytes long, or 2 to the 3rd, right? 2 squared is 4, times 2 is 8.
Oh, 2 to the 3rd bytes, like this.
2 to the 3rd byte. Yeah. Sorry. Yeah. Okay. Sorry. Yeah. 2 to the 3rd bytes. Oh, 2 to the 3rd bytes. Yes, this is in bytes. 2 to the 3rd bytes. Why do I want it in bytes? Because I want to see how many of them I can fit into a page. Because I want to page my page table. I want to have like this. Here's my contiguous. Here's my contiguous page table, and then he's going to point to another page table, and then this one will point to the actual thing that I'm interested in. That's the way I'm going to do it now. With this is 2 levels of abstraction, whatever. Two hierarchically 2 levels to get to my page.
The middle level is the same size though.
Now, but that's the key point. That's the difference here. This is no longer contiguous. This is also page. Yes, sure.
Where did you get 8 from?
8 bytes?
Yeah.
Because I said it has to be the row. I'm talking about the row. The row has to be 8 bytes, every row, because I need to fit in 44 bits in there. And 44 bits won't fit into 4 bytes, because 4 bytes is 32 bits, right? 4 bytes is 8 and 8 is 16, 16 and 16 is 32. So a row of 32, 4 bytes is not going to help me. And I always want to be a multiple of a power of 2. So I'm going to have to jump from 4 to 8. So I'm going to have 44, to get 44 bits in there, I'm going to have 8 bytes. I mean, I could have less, but I'm going to have to do it as 8 because I want to jump. I want to be able to jump. We'll see why I want to jump. We talked about that before, but we'll see again. So if this is 8 bytes, 8 bytes, 8 bytes, how many rows can I fit into 1 megabyte? How many rows can I fit into 1 megabyte?
And this is just 2 to the 20 divided by 2 to the 3.
Exactly. This is essentially 2 to the 20th, and I've got to divide it by 2 to the 3. That's how many bytes. This is 8 bytes, which is 2 to the 3. This is 1,000,000 bytes, which is 2 to the 20th. 1,000,000 bytes divided by 8 bytes gives me how many rows I have, because it's an x by y, right? So I'm just going to take 2 to the 20th. That's 2 to the 20th. This is 2 to the 3rd bytes. How in this huge space of 2 to the 20th, if I say 2 to the 3rd times 2 to the 17th equals what?
2 to the 20.
2 to the 20th. Everyone knows that, right?
Yeah.
Everybody knows.
together.
You add the two together. So 2 to the 3rd. So this is 2 to the 3rd row, 2 to the 3rd rows. These ones are also 1 megabyte, you see. This is 1 megabyte, and this is 1 megabyte. Every page is going to be 1 megabyte. So this 1 megabyte page that's going to tell me it itself is going to have to be 2 to the 20th bytes or 2 to the 17th rows of 8 bytes. True? That has to be. That's the way we want to do it. We want to have that these are the same size. What about the rows of this contiguous one?
Where's the 17 come again?
Because I want to squeeze everything into this shape that I've got, which is 1 megabyte. And I know that each row is 8 bytes long. So I want to know how many rows. So I'm just going to take the whole size and divide it by how big each row is, and I'll get how many rows I have. It's like if I had 400, if I had 400 bytes, and I said each row of my table is 4 bytes long, how many rows would I have?
Oh, so you did 2 to the 44.
Right? If I had 400 bytes, and I had each row is 4 bytes long, then I say I have 100 rows. Because why? Because take 400 divided by 4 and you get 100. So this is just the same thing. I've got here, instead of 400 bytes, I've got 1,000,000 bytes, 1 megabyte, which is 2 to the 20th. And I've got rows, instead of being 4 long, are 8 long. So I just do 1 megabyte divided by 8 bytes. But the calculation is easier if I put everything to the power of 2. Since 8 is 2 to the 3rd, I just divide 2 to the 20th divided by 2 to the 3rd, I get 2 to the 17th. Subtraction. When you do division, you do subtraction.
The number of rows.
That's the number of rows.
I thought that's the number of pages.
No. The number of pages is 2 to the 44th. That's what I got at the beginning.
Right.
The number of rows is 2 to the 44th. And we said in order to differentiate those rows, I'm going to need 44 bits. And we said that is going to have to take 8 bytes long because I'm going to have a power of 2. So it's going to be 8 bytes long.
We seem that we got stuck here though because we gave 20 bits.
We're not done. We're not stuck. This time we're not stuck.
Okay, no, but we've totally seen this before.
Yes, but now we're going to go. Yes, we have seen this before, but now we're going to finish it correctly.
Can you just repeat what 2 to 17 is? It tells
It's how many rows in our pages of this page table. Notice essentially we had this page table. It was very long. But what we're going to do is like this. We're going to make a smaller page table to page into our page table. This is our old page table that we had before. And we said when we calculated it that it would be 1 terabyte long or 4 terabytes. It would be huge. So what we're going to do is instead of making it so big, we're going to make an index into it. We're going to chop it up into pieces. And we're going to put valid, invalid over here. And then the ones that are invalid, we don't have to store. And then we don't have to store 4 terabytes of page table. We'll just store the parts of the page table that we need. And we'll only have to store this page table. But this table is going to be a factor smaller. It's going to be some factor of 2 smaller. We didn't get there yet. No? You understand that?
What's that last thing you just said? What? Okay,
This is the page table that we saw before. And we said it was too big. So what we're doing now is we're chopping it up into pieces.
Okay.
We're chopping it up into pieces. So you say, well, that doesn't help us any. If we chop it up into pieces, we still the same amount of memory. It's just now we can put it in different places. It's no longer contiguous. But we're not going to keep all those pieces because it was huge. It was 4 terabytes, but really the allocation, most of them were invalid. Most of the pages that it was referring to were just invalid. So all the invalid ones in this page table, all the ones that would have said invalid, invalid, invalid here, if the whole page table is invalid, then we're just going to mark this corresponding line, we're going to write a 0 here for invalid. And then this page of the page table, we don't even have to go there. We know everything here is invalid. If there's 1, 1 over here, then we'll have to put this as valid, and then he'll get there. But now any ones that are completely zeros, completely invalid, those pages we don't have to store in memory. We can just get rid of it because it's no longer needed. Because we know that everything there is invalid. So that's going to make our page table much smaller. But it's going to add a level of complication. And that's the complication we're talking about now, which is that I'm going to have this page table referring to this page table referring to the actual place. So this page table is not really a page table. This is really the page table. This is really just the index into the page table to tell us which parts of the page table that we had before we want. But we're going to call this the outer page table, and this the inner page table. Inner PT, outer PT. Yeah? We're going to call, that's the name we're going to call it. You really should think of it as an index into the page table. This is really the page table. Because this is not the page table. This doesn't tell us where the pages are. This just tells us where the pages that will tell us where the pages are. There's where the pages of the page table are that will tell us where the actual pages are. But now what I'm doing is some math, which is interesting to me, and you'll have to know for your exams. That's why I'm doing it.
Where did you get 2 to the 17th from?
Where did I get what?
2 to the 17th.
Because I divided 20 by, I divided 2 to the 20th by 2 to the 3rd. And when you divide powers of 2 or any powers, if the base is the same, you subtract the powers. If you multiply, if the base is the same, you can, only if the base is the same. But here we're lucky, everything is base 2, so we can divide and just subtract. So that's how many rows we have. Okay. I lost my flow of thought here. Yeah, okay. So how many bits do I need over here? Remember, this was the offset? This was the offset into here, right? This 20 bits was the offset into every single byte in this page. But this is what? What is this going to be? This is going to be, I don't have a lot of eyes here. This space here is going to be the bits that I'm going to use to tell me which row to go to in this page table, right? In other words, this is going to tell me which row to go to over here. This is going to tell me which row to go to over here. So, yeah, so this is going to tell me which row to go to over here. How many bits do I need for that? How many bits, how many rows do I have here?
20.
What?
17.
17. I have 17 rows. I have 2 to the 17th rows. I need 17 bits. So this is going to be 17 bits.
I have a question.
And these 17 bits, how many zeros, wait just a second, how many zeros will I have to add to them in order to get to the right row? As if this is 0, 0, 0, 1, if it's 0, 0, 0, I go to the first one. But if it's 0, 0, 1, I go to the second row. But if it's 001, I don't want 1, I really want the 8th byte. How many zeros will I have to add to it? 3, right? I might have to add 3 zeros to it, but that's not a problem. The hardware will just do that. Or whatever, or software, whatever. The hardware will do that. It'll add me 3 bits, and I'll get to the right row. But I need 17 bits to index into these rows. Yeah, as a habit.
Where do you get that the size of each row was 2 to the 3 bytes?
Because it had to have 2 to the 44th bits. It had to have 2 to the 44th bits to be able to access every single bit over. Sorry, it had to have 2 to the. No. Maybe I was wrong. Wait a second. Why did I say that? Maybe I'm wrong. It has to have 2. No, because no. Sorry. Because how many of these are there? Sorry, you're making me go back, and I have to remember why I got there. How many of these pages are there? Again, how many pages are there? If there's 2 to the 20th size, and my address space is 64, there's 2 to the 44th of them. So I need 44 bits to identify them. So that means each row has to be 44 bits. 44 bits is more than 4 bytes, so I gotta use 8 bytes. Everyone should look at Zahaba's notes after class.
No one can read my handwriting.
No? Oh, okay. So everyone should write their own notes. Okay.
They understand or right.
What?
I don't know how Zahaba does it, but.
Well, yeah, right. You have to be with me or writing. I know the problem. So you should write. I'll give you a pause and you can write down some summary for yourself. You can tell me, wait a minute, I want to write that down. But let's go on. 17 bits for this. So how many bits are left over? 7, right? Everyone sees why it's 17 bits for this part here? This is going to be the inner page table. Now there's this number. What is this number going to do? This number is going to tell me which row to go here, 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 which row to go to. It's going to tell me which row. Once I get to this row, it's going to be, what's going to be written over here? What has to be written over here?
Which inner page table to go to?
Which inner page table to go to? How many page? And how long is that address going to have to be? It's going to have to be, these are part of this group. Now, these pages are 1 megabytes. They're part of the general memory that I have. They could be anywhere in memory, So that means that how many, just like these ones needed 2 to the 44th bits to identify them. These ones are going to need 2 to the 44 bits. These are going to need 44 bits to identify them. These are going to need 44 bits to identify them. So these are also going to be 8 bytes long. 8 bytes. These are also going to be 8 bytes long. Because I need to identify which of all the 2 to the 44th pages I need to go to. Then I found, this tells me go to this page. Yippee, I'm at that page. But now I need to know which row to go to in that page. So I'm going to use this 2 to the 17th. 2 to the 17th, that's how many rows I've got. 2 to the 17th. These 17 bits will tell me which row to go to. Then I get to that row and I see these 8 bits again here. Those 8 bits are going to tell me which actual place to go. Then I grab this and that tells me where inside to go.
Wait, 8 bits or 8 bytes?
Bytes. What's written here, what I said, I don't know what I said. I said bits, I meant bytes. Bytes. These 8 bytes will tell, which is 44 bits. Well, you know what I mean, round it up. These 44 bits are going to tell me which page to go to. Then I'm going to grab these 20 bits and tell me where inside the page. So again, I'll say that all again. This is going to tell me which row to go to in this page table. This is going to tell me, okay, you found this row, this 8-bit address, this 8-byte address, which is 44 bits at least, or invalid, right? It's going to be 45. It's going to be an invalid bit there. If it's not invalid, then it'll take me to a real place. And now I'm at that place, but I need to know which row to go to in that place. That's going to be the 17 bits. And that'll take me to the right row. Once I got to the right row, let's change that arrow. Let's pretend it's over here. It'll tell me, go to the 3rd row, and there I am. Now I'm at this huge block of 1 megabyte. I need to know which byte I'm interested in. Now I use the third piece. So I'm essentially taking that address. I did a load word. I did some kind of load word to this address. And I'm taking that 64-bit address and I'm chopping it up into pieces. And I'm saying the last part is telling me where in this byte. The middle part is telling me which row in this page table. And this number is telling me which row in the outer page table to go to. Yeah?
Is it also the first part how many pages you have?
The first part is also how many rows I have in this contiguous outer page table. And let's answer that question now. That's going to be interesting to us.
It's 10:30. Can we take a break?
Let's take another 5 minutes or something, and then I'll take a break. I just want to finish this. So, outer page table. Again, how many bits are left for that?
63 minus 20.
64 minus 37. What is that? 20 something? 27? Here.
27.
27. Okay, so I've got 27 bits left over, which is telling me what? How many rows are in my
So 2 to the 27.
outer page table? How big is it going to be? It's going to be, here, you guys, I want some, I'm not here, I want you guys, I shouldn't say, I want you guys to say, how big is this table? The last one was 16 terabytes, which was enormous. How big is this one going to be?
So first you have 2 to the 27.
2 to the 20, this is just a practice for you guys to know how to do this calculation. 2 to the 27th, right, because we have 27 bits,
So then
times
the 8 bytes.
bytes, which is how many? We want the answer in bytes, equals something bytes. So give me 8 bytes in 2 formation. 2 to the 3.
That's 2 to the 30 bytes, so it's a gigabyte.
But the
Yes, 1 gigabyte. Yes, exactly. This table has got to have rows of 8 bytes, which is 2 to the 3rd, and it's got to be 2 to the 27th of them. So that's going to be 2 to the 30th. Remember, 10 is kilo, 20 is mega, giga. 1 gigabyte. 1 gigabyte is a factor of 16,000 times smaller than it was before. But it's still not good. It's still not good. Because we're talking, that's why I try to tell you, for 40 years, nobody ever thought you'd ever want a computer that had 64 bits. This is a new thing in the past 10 years. But for years and years, 32 bits was considered just the size that you'd ever need. Nobody would ever need bigger. Because once you start getting to 64 bits, look at these page tables. The operating system is going to have to, it's complicated to deal with this. You have to, you don't want to have a gigabyte, even a gigabyte is too big.
Is this why you need such a huge amount of RAM? Because
This is one of the reasons, but yeah, the operating system needs to be bigger to handle such bigger memory. So what are we going to have to do? Who can tell me what we're going to have to do? This is not acceptable.
make another.
Make another level. Make another level. We're not going to touch these 17 bits. We're not going to touch the 17 bits because that's how big these are. But how many bits are we going to remove? How many bits are we going to remove? Now we're going to take this contiguous outer page table and we're going to do the same thing. We're going to make it not contiguous. So I'm going to draw it like this. Sorry, Naomi. Don't worry, we'll finish. This is the last one. I guarantee you this is the last one. But this outer page table now is divided up. How big are the rows here? The same thing, no difference. Thank you. Tell me your name again. Leora. Okay. Leora says 8 bytes. She's getting sick of this. We've been doing this for a week. 8 bytes. These ones are each 8 bytes long. How many rows do we have in each of them? Remember, they've got to be 8 bytes long. Why? Why do they have to be 8 bytes long? Maybe they're different. Because they have to identify these pages. And these pages are one of the huge pool of pages that we have that are 2 to the 44th of them. There's 2 to the 44th pages. And now we've all of a sudden, and these ones are among those. To identify them, we're going to need one out of 2 to the 44th. So I need to have a number for each one. So it's got to be 44 bits, which is going to be 45 bits, which is going to be 8 bytes. So these have to be. If it's 8 bytes long, how many rows do I have? What? Leora says 17. Anybody disagree? Good. 17, the same thing, because if it's the same size, the same number of rows, got to be 17. What am I going to do over here?
Minus 7.
I'm going to take, it's going to be, I mean, I'm drawing this bigger, but it's the same size, 17 bits. It's got to be. And how much is this going to be left? 10. How big is our outer page table going to be?
2 to the 10 times.
2 to the 10th
Times 2 to the 3.
times the row, the length of the rows. How big are the rows going to be? Well, the rows have to be how big? 8 bytes. They have to be 8 bytes. Right? They have to be 8 bytes. You see what I'm saying? That's why it's so important that I wanted to know exactly how big those rows are. It has to be 8 bytes because I need 44 bits to identify these guys, because these guys are one of the 2 to the 44th pages that are out there. So these are 8 bytes, which is what? 2 to the 3rd, which equals
8 kilobytes.
8 kilobytes. Is that acceptable?
Yes.
That is acceptable.
But then now you have all the other.
Oh yeah, wait a second. No. So let's think about this. How big will the smallest program be? Smallest program. How big will it be? It just needs one byte. Let's say the program itself just needs 1 byte. Well, I gotta have the 8 kilobytes for this outer page table. And this outer page table's gotta take me to at least 1 page over here, which is another, how many? Megabyte. Sorry about that megabyte. I can't do it, can't avoid it. I mean, I could avoid it. I could change this. No, I can't. I can make this smaller. I can make this a little bit smaller, and that would end up this being, I could make this a half a megabyte easily. If I made this half a megabyte, then how big would this be? 16 kilobytes. That actually would be good, right? I can make this, instead of 20 bits, 19 bits. And then I'd have one more bit over here. It would work out the same, right? Kind of, well, it wouldn't work out exactly. We'd have to do it all over again. But it would end up being probably a better division. But anyway, I need this page of 8 kilobytes, which turns out to be the most marginal part of the equation. Then I'm going to have 1 megabyte here, but I have to also have 1 megabyte here. I'm going to also have to have 1 megabyte here, so another megabyte, and then finally to the actual page where it's at, I'm going to have that allocated. So the smallest program will have to be how big?
1 megabyte.
No.
3.8.
3 megabytes plus 4 kilobytes plus 8 kilobytes. After the minimum program will be 3. And what other disadvantage do I have? But first of all, that's not so bad. The minimum program will not be before we were talking about a minimum program being a terabyte. Now we're talking about the minimum program being 3 megabytes. It's okay, still big, but we could improve it by changing the numbers around, right? I think we could improve it by making this 19 and then working it all out again. So the minimum would be 19. What other disadvantage do we have? There's one other disadvantage that's important to have. What other disadvantage
Is
do we
the
have?
time to go from table to table to table.
Thank you. Everybody heard what Zava said? The time. In other words, if I want to just do a load word, simple load word, I got to first go to this, load this memory location. Then I got to load this memory location. Then I got to load this memory location. Then I got to load this memory location. And that's going to slow us down terribly. So so what's the trade-offs here we've had? What we've seen is that if we kept our pages at 16 terabytes, it would be faster. We'd have fewer jumps. If we make a lot of jumps, we save memory, but we lose speed. So this is a classic trade-off in computer architecture and operating systems, which is the trade-off between speed and memory. And that's why you say, if you have more memory in your computer, it'll run faster. Exactly this point. If we don't have enough memory, we're going to have to do slower procedures to get to where we need to get to. If we have more memory, we can do it differently. So there's always a trade-off in everything. Also, if you do like algorithm research, and you're talking about an 8's binary or something, it's faster, but it's going to take up more memory than other things. There's always a trade-off. Different algorithms for sorting or for the ones that are faster usually take up more memory. It's always that trade-off. Okay, wait a second. So what's the best solution? So what can we do to improve this? What can we do to improve this? So we still have this problem, right? We still have this problem of slowness. How can we improve it?
Can you just have the computer pretend it's 32 bits?
Yeah, you could do that. You could do that. You could say, but then you can't allocate.
And you're ignoring half your memory.
Yeah, you ignore not half your memory, much less than that, much more than half your memory. You're 2 to the power of 32 of your memory.
But then,
Almost all of your memory you're ignoring.
but could it be like the operating system could view it as if you have like 2 separate memories? You have
Yeah, I understand what you're
you
saying.
have like a
There's
32
one
bit and a
program,
32
each
bit.
program will think it's running on 32 bits, but they're all separate 32 bits. You could try to figure out something like that, yeah. That's not the direction I was going in, but yes, you could do something like that. That would be, you'd have to work all that out, and that would be a good paper to write. How exactly you would do that. But yeah, you could do that.
That way every paper.
Sure.
But what other thing can we do? What did we see in architecture? How do you make things faster in architecture? What's the word? Somebody said it actually today. Cache. You could cache things. In other words, a memory lookup is slower than cache. Remember from architecture, cache is something faster than memory. So we could cache things. We could put things in a cache table. But we'd have to cache, what would we cache exactly? That's an interesting question. What would we cache? Yeah, well, whatever. We would cache these things. We would cache these things. Simplest, without getting too complicated. We could throw a cache in between here and here. Instead of caching going to the memory, he would go here. But then still we have to go from cache to cache. It'd be nice if we could do it all in one cache. We could probably. In other words, what observation can we make? We can make this observation that usually, Usually a program is local. There's locality. We're going to talk about this in continuation lectures, but there's something called locality, which is that usually a program, it goes line, line, line. You don't like jump 1,000 lines forward and then 2,000 lines forward and then 10,000 lines backwards. Usually you go line by line in the same local area. Like a normal person usually lives, even if he lives in New York City, he most of his things he does is near his house. He goes to the supermarket. Occasionally he goes to visit somebody, but so a program is usually, so it could work out that we could cache this whole block of memory, or not this block of memory. We could this line, forget that, not the whole block. This line and this line and these lines and just say, well, he's gone here, he's probably going to go that route again. All right, so we'll stop here from a break here. But that's the basic idea of hierarchical memory, and we see that the more hierarchy you give, the smaller the page table gets, but you lose this point of jumping. Okay.
Would you mind repeating what you got 8 kilobytes from?
8 kilobytes is because it's because of here. I took off 17 bits for the next level to identify each row here. These 17 bits are each row here. These 17 bits and if I have 64 bits, I'm left with 10 bits. 10 bits is going to be the outer page. So theoretically, the outer page, what you might say, is 2 to the 10th, which would be 1 kilobyte. But we noted that each row is not 1 byte long. Each row is 8 bytes long. So it's going to be 8 times 1 kilobyte, or 8 kilobytes. Yeah, that's the number of rows. How many rows are here? 1,024. 2 to the 10th. All right.
How long of a break are we taking?
Let's take a 10-minute break. And I can turn the recording. Pause.
No, you can't pause it, you only have 10 minutes.
How much time do we have? 10 minutes.
10 minutes. Haha, I was.
You're distracted. Okay, we're starting.
No, she was not.
Here's some girl.
I wasn't willing to resign because then I'd lose the
Share screen. Now you can all relax. We're back to our slides.
Can you either erase the board or pull down the thing?
Yeah. Okay, so well, we're not done with pages, but we are now of the PowerPoint. Here, you see, they do kind of this same kind of calculations that we do, but I do mine better. Okay, free frame. There, just this should be obvious, but I'll say it, which is there obviously is a free frame list. In other words, when I'm allocating memory to a process, I have to, the operating system has to keep track of which pages are available and which which pages are not available.
Did we do this already?
I don't think so. Maybe.
We're up to, we just did the hash tables.
All right, but all right, well, okay, but I still, really? We talked about TLBs? You all know what TLBs are? No, I think maybe we skipped, I think we
Yeah.
skipped something. We did TLBs? Transfer look-aside buffers?
Yeah,
Yeah,
I have notes on them.
okay. Yeah, we did do it. Okay, so let's go. Maybe you're right. All right, and so then you all know about valid bit, invalid bit. Okay. Shared page, hierarchical. Here is the outer page table. Yeah, two level. This is a two level. This is two level, right? What we did just now, before the break, was three level, right? We ended up at three level. This is two level. Here, wait a second. Yeah, here you see they divide the page into two parts, and we were discussing why exactly it's 10 or not 10. And I came up with how I defined how this should be. The size of this is determined by what we just said? It was 17 in our example. By the number of rows that can fit into whatever our page size is, based on how long the address is. This is a 32-bit example. And here's that jumping that we're talking about. He talks about 64-bit also. And this is where I added a slide. And here is more and more divisions here. This is still kind of crazy. How big is the second outer page table in this slide? Minimally.
2 to the 32.
2 to the 32 times some number of rows, which is going to be big because how big is it going to be? The offset is only 12. How big are the rows going to be? 52 bits, 8 bytes long. Again, it's going to be 8 bytes. So it's going to be 8 bytes times 2 to the 32. 2 to the 32 is how much?
4
Mega
4
giga.
gigabytes.
It's going to be 4 giga times 8. 8 times 4 is 32 gigabytes. So this is insane also. Mine is reasonable. This is, by making his pages very small, his outer page is going to be 32 gigabytes, right? Yeah, 32 gigabytes. We talked about hash table. You're right, we did talk about hash table. All right, so now we're going to do inverted page table. Now let's see what is an inverted page table. Remember what hash table is? Wait, before we get there. Hash table is, seems like a good solution. We have some kind of hash function, and our hash table can be any size that we want. It can be very small. What's the disadvantage if it's small? The smaller it gets, what gets bigger? The linked list. The linked list gets bigger. The linked list is going to require what? Hopping, right? Every jump in the linked list is a memory read. So we're essentially, again, saving memory. The hash table gets smaller. So we're saving memory. We're losing speed. We have to make a lot of jumps. But if programs are very small and only need, let's say, a few pages of memory, probably our linked list is going to be very small. So a hash table could be a good solution. Hash table really, I would have said that hash table is the way things work nowadays. But the guy at MIT said that they work with, he said most of them work with these multi-layered paging, hierarchical paging. So I was surprised to hear that. I don't know. All right, so let's talk about inverted page tables. Up until now, this is a rewritten slide. Up until now, we have described a system where each process has a page table capable of referencing every possible memory location, right? Up till now, we were describing a system where we could reference every single page in memory. Whichever frames the process was not using had to be marked as invalid. So we know we can't go there. Let's do it backwards. Well, what does that mean? Instead, each process, or in other words, the operating system could keep a list for each process. I wrote it in shorthand here. Each process could keep a list. Obviously, the operating system is keeping a list for each process of the frames it is using. Just keep what you're using. Just have a list. You're using page number 100 billion, you're using page number 50 billion, whatever pages you are, just write them all down and just keep that. It sounds a lot easier. All other frames are implied to be invalid. If it's not in the list, it's invalid. This page table will obviously be smaller. It'll just be what you're using. There'll be the minimum amount of size it should be. Or you could have one page table. There's another similar idea, but the same idea, but a little bit different. The operating system could just have one huge page table for all the processes. And this page table references all the frames. But we still save memory because we only have one instance of each page of the page table. In other words, we could say, oh no, let's have one page table for every frame. And let's have one for the whole system. But then what will we lose? We'll have to say this is for process 1, process 2. On the row, it'll have to be labeled which process. What else? All right. Let's stick with the first idea. That for each process, we keep a list of what it is using. And so, but in this second scheme, each entry consists of the virtual address of the page stored, of the virtual address of the page stored in that real memory location, with information about the process that it owns. Okay. This saves memory, but increases the time needed to search the table when a page reference occurs. That's the key line. Again, we're going to save memory, but what are we going to have to do? We have no idea when we want wait a second. Right. How are we indexing this? In other words, we used to jump into the page table. How do we jump into the page table? We simply took the bits from the address and used that to tell us which row to jump to. Now we can't do that. We're going to take the bits there and we're going to have to search through the page table and see if it's there. You understand my point? In other words, we no longer can rely on, he says he wants to go to address 10,000. That address 10,000 may be in our page table. We have no, how are we going to know if it's in our page table? Maybe we really gave him that, page. You understand what I'm saying? In other words, we have a page table of every, because we used to say, go to row, 5, and this is the address that you want to go to physical memory. Go to place, 10,000. I don't know. And this one, if he says, here it says go to page 500. If he goes down to here. But now, I'm going to have, I'm going to have this skin, load word, 08. I'm going to have load word 08. Normally, I would go down and count 8 places. And whatever it says here, I'm going to actually load 10,000. This is the 8th place. And I'll go to this one. Now he's going to say, go to the 8th place. And I can't know that it's here because it could be the next time he'll say 10,000. If I wanted to have this number directly correlate to here, then I have to have every possible number that he could write here valid here, but it doesn't exist. So what I'm going to have to do is in order to look for 8, I'm going to have, these rows are going to look different now. These rows are going to look like this. This would be 10, 10 comma, 500. And this will be 8 or 18 comma 10,000. And this will be 8, 514, for example. What does this mean? This means that if he wants page 10, it's in location 500. If he wants page 18, it's in location, it's really page 10,000. If he wants page 8, I'm going to have to search through the whole table before I know that I don't have it there. And then once I find it's not there, I'll say, oh, it's invalid, and I'll throw a memory exception. But I'm going to have to search through the whole table to find the one I want. You can say, well, just put them in order. But then I'll still have, yeah, I could try to order it. I could try to order it.
Well, but which numbers are you ordering?
But I'd still have to search. Even if it's ordered, I'd have to do a binary search, right? If it's ordered, which numbers am I ordering? I could order what is going on here? This is the virtual, what am I writing? Virtual address. In other words, what the program thinks he wants. And this is the physical address, where it actually is. Physical address.
So what's the point of this? You're just creating more problems.
No,
You're still searching for something.
No, because if the program is very small, then my page table is like that. And I only have 3 things to search. And if he wants, right? And anything else, if he says, give me page 17, what is going to happen? It's going to say invalid. I'm going to throw an exception. If he says, tries to give me page 25, it's going to say invalid. If you ask for 8, it's going to be valid. He's going to search for it. So that's the idea of an inverted page table. It sounds great. The only thing is it requires searching. Also, look what I wrote, but how to implement shared memory. The last line on the slide there. Can anyone understand my question?
What are you sharing memory between?
Well, between 2 processes. If you remember, when we talked about paging, we said one of the advantages of paging is that 2 different processes could have the same page marked as valid. Let's say they both want to use the string copy. Naomi, with me?
Yeah.
Let's say they both, so leave your mouse on. Let's say they both want to access a string copy is a library function. So the string copy has to be in memory. But if 2 processes want to use it, we can just mark them both as having access to that memory spot, and they can share memory. That was the idea of paging. How will we implement shared memory? Well, I don't see the problem. There's no problem. So we'll just also put a entry for it.
But could you just have like 2 columns?
I don't see
of-
that's why.
of
I don't know why
virtual
I wrote
memory?
that question. Yeah.
You just have 2 columns of the virtual addresses, but then they'll just correspond to the same.
Same place. Yeah, exactly. Each process. I know why. Because remember, there are 2 different ways of doing it. If you have a page table for each process, then fine. But the truth is, the book is really talking about the second way, where you have 1 page table for the whole operating system maintains just 1 page table of all the valid pages, and then you search everywhere. And then, how would you have? In other words, how would that page would be listed, have several processes that have access to that page, you see, and that would be weird.
It's listed per process
It's-
or per page.
The book is thinking about it in terms that you'd have every page that any process is using is listed in the page table, and you just have 1 big page table, and then the page table would have a 3rd field in it. It would have a 3rd field, PID, process ID. And this would be, for this one, it would be 1, 1, 2. And then so when process 1 comes and asks for page 18, he'll find it. When process 1 comes and asks for page 8, it'll say invalid, even though 8 exists. Because 8 is located there. But it could be that it'll actually have like this. If you have 1 page, it could look like this. 5 here. PID 1, you see? That would be legal. If I have 1 page table for the operating system, then I could have 2 virtual 8s. Because the ID, which process we're talking about, would be different. But the problem is now, how do I do shared memory? Because what if at page 8, they both want to have I guess I could do it. I could do page. Why can't I do it? This could be the same number, 66. This could be 5. This could be 560. That his string compares over here, and his string compares over here, but it's the same string compare. If that's 2, let's say. whatever. You could do, I don't see why it's a problem with shared memory. All right, so here's an inverted page table. So the CPU, you see how here we have this new thing, PID? Again, the book is thinking of a single page table for the whole system. I was thinking, well, you don't have to do it like that. You got a different one for each process. It makes more sense. But if you do it this way, then you have to have a PID. You have to search for the PID. First thing you got to do is find his PID. Then you got to find of the PIDs, the one that's the P matches the P. That is a virtual page that he's looking for is here. And then he's doing a little bit differently. Look how he did. I'm sorry. He's doing it differently. My explanation was that you'd have all the information on a row. You'd have this and the conversion. How is he doing it differently? Can somebody tell me how he's doing it differently? I said, you'll search for P. This is the P here. You'll search for the 8, and then you'll find out what the address is.
So here it will only look and check the P. If the P, it will go down the table. If the PID matches, it will check the P. If not, it will just skip it.
If it doesn't find the P, then it'll say not invalid, that's for sure. But what is that I there? That I, look at that I over there. Where'd the I come from?
Is that the jump from the beginning?
Yeah, that's very weird what he's doing here. You see what he's saying? Saying how far down I had to go to find that thing. That will tell me where it is in physical memory.
But is it continuous?
I don't see what the point of that is. My method is much better, right? Where I just keep track. This is really inverted. Why is it inverted? Because he's saying, I'm using the amount that I'm not storing also the virtual address. I want to keep this, I'm using the amount that I go down to tell me where it is in physical. But that means if I want to go to place 1,000, then I'm going to have to, that means I have to search everywhere. And in other words, there'll only be one location where virtual address 1,000 can be in this page.
Is this assuming that the page table is contiguous?
The page table has to be contiguous and it has to be quite large. This page table has to be contiguous and quite large because if I want to go to address 1,000, it can only be in row 1,000. My idea, what I wrote here on the board, is that it's much more flexible. I can put anything anywhere I want. That would be a better way to do it.
Same thing in this?
What?
The P's both are the same P?
Yes.
And so what it's just seeing is like, okay, we're gonna match the PID and the P, and then once we have that, then we'll just see how we have to get here, and then that's what we're gonna use that information.
Yeah. Let me raise this for a second. I want to show you what this diagram means a little bit better. Right. I mean, you should know. In other words, it's good to understand how to read a diagram and understand what it's saying. So I'll go through that. Let me just present. So what this is saying is like this. Here. Just to be clear, PID Q. Okay, look at this. This page table is as big as total memory. This page table represents all the memory of the computer, just like we said before, so it could be very large. If I am PID, that's his number, that's his process ID number, I'm going to look at all of the entries that start, 3 colors, and all black.
I think that makes one color.
Yeah, that's a joke. That's a reference to to Ford. You know Ford, the guy who invented the Ford car,
Yeah.
Henry Ford. So the famous quote was, he's an anti-Semite, but the famous quote of his was, "You can have a Model T in any color you want as long as it's black." So I'm just saying, I was making a joke to myself that I have 3 colors, they're all black. What? Oh, you have, it's okay, I'll start. Thank you very much. PID, why did I put a star here and here? Because those are the ones that are valid for this guy, for PID. PID2 is another process. PID2 is another process. So I'm gonna search down every single guy that's PID, and I'm gonna check. Is this the P I'm looking for? No, this is L. It's not. And this is P means just a number, like 17. L is a different number. Is this the one I'm looking for? Ah, yes, I found it. That's. Oh, sorry. That should have been. Sorry, here. Here I found it. PID P. So no, this one is not valid either. But anyway, he's gonna, before he even gets there, he's gonna say, oh, here, I found it. These are the 3 PIDs that are relevant to me. And I'm gonna have to check all of them. And I found it. And the fact that it is I rows down tells me that it's in physical location I over here. I'm gonna take if I went to row 1, row 2, row 3, row 4, this is gonna be a 4 here. And now I know the physical address of my process, because I was looking for P, but it's really 4, let's say P was 7, it's really 4D, whatever the offset is. If the offset was 0, 1, then it's 0, 1. So I'm gonna go to the physical memory location, this. Why is this? So what's going on here? I have every single, if I want to map, why is it inverted? Because if I want to map physical location 4, it must be on row 4. It has to be on row 4. But I don't know when I'm searching for it. I don't know that I'm looking for row 4. I have no idea. I have no idea where P is. I'm looking for P. P is, let's say, 0. I'm looking for the first memory space of my program. But it could be, I have no idea where it is. It could be, it's really at 401. But I'm gonna have to go through all of these till I find it. I check all the ones that are marked PID, and I say, oh, this is the one that's the same P as this P. So now I know how far I've gone down, and that tells me how far it is in memory.
How could more than one process have the same PID? Why would we have an example of PID with one thing and PID with another and PID with another?
Because he has 3, PID
Is it all the
has,
same process and one is the start?
no, because he has 3 pages allocated to him. In this diagram, PID has 3 pages allocated to him. He has page L, page P, and page Q.
So one is where it starts, one is, and the rest of it.
In other words, what?
And so PID with P is where the beginning of the program is for that process.
Gabby just asked a question.
What?
She
Read it.
said, if you were to jumble up the rows or order them, would that not give you a different I, which
You can't double up
give
the
you a
rows.
different address?
Yeah, you can't double up the rows. No, you can't. No, there's no doubling up the rows. You're right. There might be some computation. If these rows are very long, the I might have to be. You might have to take the number of rows and multiply it by something or divide it. The book in general never discusses that question about whether the I needs to be some mathematical manipulation to get the actual right number. In other words, how much you go down could be not exactly corresponding to this. It could be you have to multiply it by 2 or add 2 zeros or something, or remove 2 zeros. That's not
She
important.
said jumble up, like change the order.
You can't change the order. The order here is fixed. The order here is fixed. In other words, that's exactly what's going on here. Gabby's asking a good question, but that's exactly what she understand. The question shows you understand what this diagram means. What this diagram means is that if I want virtual page P, I have no idea where it is when I'm looking for it. But when I do find it, it can only be when I do find it, the location it is in the row tells me where it is in physical memory. So if you think about it from the other way around, from the operating system, let's say I have this program and I want to allocate memory space, maybe instead of calling this P, let's call this 1. Here, let's go like this. Process, he has 1, 2, 3, and he has 1, 2. Okay? So process 2 has a page called 1 and 2. Process 0, or process PID has 1, 2, and 3. Now, why are they in these locations? Because let's say process PID came and said, I want process 4. So I'm going to go to memory over here and see where do I have something free. And I'm going to see I have something free at location 12, etc. So I'm going to, and I want to give it to process 1. So I'm going to have to count down now. 1, 2, 3, 4, until I get to 12. And then I'm going to say, here, PID, here is where I'm putting the free page that I gave you, your page number 4. I'm putting it at row 12. I had to put it at row 12 because that's where the free memory that I allocated it was. So now when you go to look for it, you'll search all the things that are PID until you find one that is matching your 4 that you were looking for. And you'll find 4, and it'll be, because it's down 12 rows, you'll know to go to physical memory 12. That's why it's inverted. Because I'm not searching, my search is on everything, but my result is the fixed number that tells me where to go.
How is this helpful? Oh, sorry.
How is this helpful? This is helpful.
Like, because your thing was helpful because
Mine was
didn't have to
better.
use the
Mine
entire
was
memory
mine was
store.
better because I could have a page table very small. This is still helpful because, and also the searching in mine was very small. I have small pages and each one, and however many with my search would be limited by how many I had. And if I don't find it, then how is this helpful? This is helpful.
You're gonna have to search through all of memory to find something.
You have to search through all the page table. Yes. This is kind of bad. Yeah. Not only is the page table large, not only is the page table very large, but you're going to have to search through you have no idea where it could be. 4 could be over here. 4 could be anywhere. I have no idea where 4 is. 4 could be anywhere where the PID is valid. Well, yeah.
Can you start
Yeah.
checking from the
It's not a really good, I don't see the advantage of this over either the multi-level page table with cache to speed it up, or what I suggested of an inverted page table where you keep it small and you have it for each one. But this is the way the book understands it, that they have a long page table of all memory. But no, so what's the advantage? The advantage over the regular one would be that here I have only one page table. That's the advantage. I don't have the other system. I have to have and maintain a full page table. I mean, if you think about the original one that we have, page memory with no hierarchy, just one page table, and that's it. Then I'd have the same size. This is much better than that. I'd have the same size, but I'd have for every process, there'd be a whole new one. Here I have one for everybody. The disadvantage is still against that one, against that terrible one, where we just have one level, is that now I have to search everywhere. So again, I save memory, but I slow it down because I have to search. But I could have a cache. I could again have a cache. While I'm running him, I could cache certain rows that I've hit before and use them again. Yeah.
Would you be able to start searching from the right side?
That would be meaningless if I search from the right side because there's multiple 2s.
Yeah, but then then.
What would I
then
search for?
Let's say it's a 2, then you.
I would search. Oh, you're right. I could search for all the 4s, and there's only one 4, and I find it. But I'd have to still search everybody because I don't know. This could be a 4. This could be a 4. I don't know who's going to be a 4. I'd have to search every row anyway. Not gonna help
Then
you.
when it comes to, let's say, PID, then you have, if you start from the right side also there, can you do that?
I could start from the right side. And then I would get. But I have to search everybody. I could also start from the left side and have to search everybody. That's not going to help me either way.
No, but the right
Either way,
side
I need to
works.
find a matching pair. I need to find somebody who's got PID and the 4. And there's only one of those. And I have no idea where he is. So I have to search every row. Doesn't matter whether I start from the right or the left.
Why would you have
PID 2 and PID 1?
Because this is representing all the processes on the system, not just one process. So I have to identify which process this page is referring to.
Even though it has the same PID, it's different processes?
No, this is the same process. These three, the ones with the stars, are the same process. He's got 4 pages allocated to him. The name of his process is PID. The other one is PID 2. He's only got 2 pages allocated to him. But this page table is maintained by the operating system, 1 page table for all the processes.
What does the 2 tell us then? Like,
What?
so what does the 2 tell us?
The 2 tells, that's what he was looking for. If I say, please give me memory address 201, then I know that I'm looking for page number 2. So I'm going to go, and I also know that it's PID. So I'm going to search for PID, and it's, oh, lo and behold, it's here. Now I know that this is my I. I'm going to put that over here, and it's not going to be 4. It's going to be, let's say, 3. I don't know, whatever that amount is. And then I'm going to go to offset 1.
Okay.
But you're doing so many comparisons because you're comparing the PID. First you're comparing the PID, then you're comparing to see if the P matches. But how is that a good trade-off? There's so much.
Yeah, it doesn't seem so
Like
great.
it's like there's no
There
benefit.
probably is
There's no benefit of space, like of memory.
Well, if you remember in architecture, we have ways of building hardware that would search. We don't have to do a search by a loop. We can search through hardware.
Like a parallel.
Parallel search. We could do a parallel search. Still would be very big. It'd be a lot of hardware to do that on a huge page table. I don't think it's practical to have an inverted page table on a large system unless you do the way I said in the beginning. My way was small page, which with small with individual inverted page tables for each one. But then it wouldn't really be an inverted page table. What I did is not really inverted. See, the inverted is the I. What I was doing before in the beginning was really not inverted page table. It was really just, I had 3 pairs. I had this, and then the number. Instead of using I from this, I just wrote the 3 over here. I just made long rows in my page table, which had all the information I needed. That would be actually a reasonable way to do things. All right, let's go forward. End here.
Oh, we're not continuing it?
I have more slides, but this is just, these are examples. I'm not continuing it, no.
We have the old version. Where do we end? Just like where
Well, and,
after here, or before, or from?
sorry, end here, after inverted page tables.
Oh, there aren't any new slides yet on.
Yeah, so I'll put them up. What am I gonna do? Here, let me stop the recording. You're the teacher. Okay. All right, so we're going to talk about the next step, basically. The next step in everything we said. Up to now, we talked about that the memory is page, right? Let's go back to the page memory, right? We had page table, we had inverted page table, we had a hash table maybe. But once we have these pages in memory, and they're pages, we can move them around as the program is running. You understand what I mean? In other words, you have a page. Imagine that picture we had before of this page is physical memory location 10. This page is in physical memory location 20. I could take a page and put it on the disk that I'm not using it right now. And then when I do need it, I'll bring it back from the disk and I'll put it in a new location. And I'll just change my page table entry and the program will continue running. In other words, once I've got this idea of a page table, I don't have to guarantee that all my memory is in the computer all the time. I can have some of it on the hard drive I can use the hard drive to put a page that I haven't used for a long time. I'll put it on the hard drive. And then when I eventually need it, I'll bring it back into memory and I'll simply mark its new location in the page table. So when the program wants to access that page, he'll check out the page table and go find it. So by having pages in a page table, I have now gained a new ability, which is to have virtualization of memory, which means using the hard drive as a place to store pages that I'm not currently using. All right, so let's go slowly. I just explained the overview of what I'm doing, or what we're going to talk about. So background. Code needs to be in memory to execute, but an entire program is rarely used. So wouldn't it be nice if we didn't have the whole program in memory? For example, error codes or unusual routines, some function that I only use once, or large data structures. If I have some huge array, I don't probably need part of it at that time. So it would be nice if I didn't have to have it in memory all the time, because then I could have more programs running at the same time. I need less memory. So that's what's called virtual memory, and that's what we're talking about now. So entire program code not needed at the same time. In other words, sorry, I don't need all of them, even though I need to have the whole program in memory. I don't need to use it all the same time. I'm only using one row at a time. Perhaps I could execute a partially loaded program. And then the program would not be constrained by the limits of the physical memory. Now, if the memory was only 18 gigabytes or 16 gigabytes, I could have a program that's 20 gigabyte size and just bring in parts of it that I need and then put the other parts on the disk. That's what it says here. Programs could be larger than physical memory. So virtual memory. That's what we're talking about. Separation of the user logical memory from the physical memory. Only part of the program needs to be memory execution. Logical address space can be much larger. Allows address space to be shared by several processes. Allows more efficient, more programs running concurrently. Because you have now the same memory, but if you have, let's say, 18 gigabytes of need, you have a program that needs 9, another program needs 9. So normally if I had 16 gigabytes of memory, I could only have one of those programs. The one of the 9, one that needs 9 would run, the other one would have to wait. Now I could say, no, I'm going to put both of them in and just have the parts of the memory that they need in memory at the same time. So let's look at this picture. And this picture explains what I'm talking about. So here are the virtual pages. This is going back to the regular virtual page. What is this? Virtual memory that is larger than physical memory. So here's my physical memory. And yeah, I don't know. All right. Here's my virtual memory. I think I say I want to go to page 2. And he comes over here and what is this? Well, I don't know why the arrow goes to here. This is, yeah, I don't know if I like this picture so much. Let me change this picture a little bit. What is this virtual memory page here? This is the memory that a program wants. And this is like a page table. And he comes and he says he wants this location. And it says, oh, go over here. Here's the mapping. Here's the page table. And this says, go to this location. And this is the physical memory. So that's what we had before, right? In other words, says, virtual page 7, you know, and this is going to say, go to frame 10. And here is frame 10, and he got his memory. That was our mapping system that we had up to now, right? We said we had some kind of range of virtual memory, all the possible memory places, and he says, I want frame virtual page 7. We went to our page table, and it said, oh no, you got to go to real frame 10, and that's where, and then in the offset, etc., all those details. We're not giving you all the details, but we also now have the possibility that he says, I want virtual page 8, and he says, oh, okay, go here, and instead of saying go to frame 10, he says, you know, invalid. You know, there's a validity bit, and it says not in but this validity bit doesn't mean it's invalid. It's not really validity bit. It's really not in memory bit. This page should be in physical memory location here, but it's not there. I know it. He'll have to mark that he knows, don't go to that place because it's not there. Where is it? It's really on the disk. So you have to, before you can access it, we're going to have to copy it into this location. Now I'll tell you it's there. I'll change the bit to valid. And now you can go and read the memory. I'm going to have to bring it from the disk. Well, what does this give me an advantage of? I could have, theoretically, from 0 to 20 virtual memory, but my physical memory is from 0 to 15. That's all the memory I have, 15 pages. So I'm giving things small just to keep it simple to understand. But I could theoretically, now if I say I want to go to page 20, the mapping will say it's not there. So it'll bring it in and it'll say, okay, I brought it in now. Your page 20 is here and I'm going to put it over here. So now the mapping will say go over here and get it. So the physical memory doesn't have to have the ability to have every single page in memory at the same time. If let's say all the spaces are filled, what if they're all filled? What if I've got frame something, frame something, frame something, frame something, frame something, frame something? Yeah, these are all occupied, frame 8, frame 25, whatever frames there. And all of a sudden he says, I want page 20, and it's not in memory. So then he's going to have to take whatever is here, or he's going to choose somebody, which we'll call our victim again. We've talked about this. We talked about a similar thing before. What was the Zahava? What was the parallel thing we talked about? A victim, not page, whatever. It's a similar concept that we saw before.
Nothing.
Yeah. Time's up.
Yeah, people's class.
Okay, but let me finish this one point. So theoretically, I couldn't put all of this into the physical memory, but now I'm asking for it. I can bring it in and put it here, and he'll be able to access it.
What is something overrated? Like if we're not storing everything in the physical memory, but we need something that's not there, but physical memory is full, then what do we do with that?